Hello and welcome to this UniTaster OnDemand event today, where today we're going to be exploring electrical and electronic engineering. With these events, what we try and do is support students by providing information about subject areas so you can go on to make really good university decisions in the future. So whether you're watching this directly or watching this as part of your school, a really warm welcome to you. My name is John Cheek. I'm the founder and director of UniTasterDays, and I have the easiest job of all because all I do with these events is introduce our fantastic speakers. And today I'm joined by Professor Nigel Schofield, who is joining us from the University of Huddersfield. Nigel is a professor at the University of Huddersfield and also is an academic on the programme, and he's going to talk to us about studying electrical and electronic engineering at university. Over to you, please, Nigel.
Hello, everybody. My name is Professor Nigel Schofield. I'm a professor of electrical engineering at the University of Huddersfield. I'm going to give you a bit of a history lesson about my career and what I see looking forward in the next 5, 10, 20 years with a crystal ball, if I can, into this area of electrical engineering and electronic engineering, as I think it may be expanding in the UK and of course worldwide as well. I'll just talk about myself a little bit. So this is a bit of a history lesson, if you like. This is me, Professor Nigel Schofield. Academics always enjoy talking about themselves, so let's talk about me. I left school at 16, and I worked as an apprentice electrician with the National Coal Board. I was working in underground coal mines, where I learnt the trade of an electrician. Working on electronic systems, and during my time in the industry, it became clear to me that the industry was starting to be run down, and also my qualifications that I had were not sufficient to take me further on in my career. And so I looked at doing a BEng degree, and I did a BEng honours degree at university because I wanted to learn all about electrical engineering. And after finishing my degree, I then realized I wanted to learn more. So I did a PhD in electrical machines, actually, for electric vehicles then. So very early days when we were starting to consider electric vehicles. I'm also a fellow of the Higher Education Academy. So that's a qualification in terms of my teaching skills there. So hopefully I'm a good teacher. I also have professional qualifications then. So one thing that a degree gives you, it gives you the academic requirements to satisfy professional qualifications, providing your degree course is accredited. If you wanted to stay as a professional engineer in the industry, then make sure you look for a degree course that is accredited. After graduating my degree and some years of experience, I then applied for a chartership. I became a chartered engineer sponsored by the Institution of Engineering Technology, the IET, and registered with the UK Engineering Council. So again, the requirements for chartership are it's now an MEng degree with an accredited institution, then followed by a few years of industrial experience. So one thing that I've learned during my career is, and this is some key advice that I want to give you, is try to open doors and keep them open. When I did my apprenticeship, I realized that I was stuck and I couldn't progress further as I looked around for other jobs. My career was constrained. And so I tried to open doors, and the best way to open the doors is with qualifications. And I did a bachelor's degree then. And now I would also consider doing a master's degree, and out of interest, I did a PhD as well. And I find that those qualifications have opened lots of doors for me in my subsequent career. I've never been unemployed in the whole of my working life, and that I think is underpinned by having qualifications that get you into certain jobs and positions. Yeah. Bit about the history lesson then. So I was an electrical power engineer, and this is a coal-fired power station. Inside this room here, this is full of electrical generators, There's 4 500 megawatt machines, electrical machines. The station generates 2,000 megawatts, about 3% of the UK's demand. Lots of electrical engineering, electronic engineering, and control systems engineering on this plant here. The stuff coming out of these towers here is steam. It's just steam that you might get out of your kettle. But the stuff coming out of this tower here, you may think the bulk of this is emissions, but this stuff coming out of this tower here are all the nasty things which are byproducts of conversion of energy from, in this case, coal into steam energy, and then from steam into mechanical, and then mechanical driving electrical machines to electrical generation. So this is the waste gases and essentially lots of different effluents coming out of here that have been cleaned up over years. One thing that cannot be really well addressed is CO2 emissions. So when I graduated in 1990, the UK electrical generation by coal, that the industry that I'd previously worked in, was about 65% of all the electricity in the UK was via coal generation. In 1990, the industry was privatised. 4 years later, that share had dropped from 65 down to 35%. The remaining taken up by new gas generation that was built over 4 years. So a very short time period to change from one energy source to another energy source. And that's an interesting point, I think, going forward in the future as we talk about decarbonising our society and getting rid of CO2 generation. Now our task is to get rid of the gas generation that replaced the coal generation back in the early 90s. In April 2017, there was actually one day when there was no UK electrical energy generated by coal for a complete day. So that was the first time really since the start of industrial electrical generation back in the 1880s, 1890s. So think about that. This power station here was built in the early 1960s, and for 30 or so years, well, it's just been decommissioned now. So yeah, 40, nearly 45 years it's run there continuously, turning coal energy into electrical energy. That's finished now. Okay, it's very interesting if we think about going forward. This year, how much electrical energy will be generated by coal? Have a look on the internet. There's lots of information about this, and you can see how the electrical generation by coal is very much reduced. But we still have quite a large element, 35% by gas, which is a CO2 emitting energy source. So have a think about that, and have a think about in 4 years' time. You know, government's talking about changing things to go from carbon-based fuels to other type of fuels, other sources of energy resources. And then think about what's it going to be in 20 years' time, maybe when you're in mid-career, where you've left school, you've got some qualifications, hopefully, you've graduated with a degree, and you're in industry, you're in your engineering position, mid-career. What will be the energy mix then? It's very interesting to think about that. It is a very big problem as well. If we look at this power station here, look, what do you notice between the two power stations? Okay, well, this is Ratcliffe-on-Soar power station. It's in Northamptonshire, and this was a picture taken in September 2019. And just compare the two. What do you notice? Well, there's no steam coming out of here, and there's no emissions coming out of the tower. I stopped at the side of the road to take this picture because this really amazed me. So this is the first time that I'd ever seen this power station not generating. So it's a similar design, 2,000 megawatts, 3 or so % of the UK's electrical energy, and it's not working in September. No steam output, the station is effectively turned off, and it's the first time since around about the 1960s when these stations have not delivered electrical energy into our electrical network. So if we look at just a graph of energy demand, this is in the UK, this is electrical energy demand over time. Look, you see I graduated in 1990, a very rapid change then from 65% coal to combined cycle gas turbines, so gas generation. Nuclear stayed pretty consistent, around about 16%. Virtually no renewables. 10 years ago, the same sort of mix, about 35 thermal, which is coal and other bits and pieces, about 35% gas, about 16 to 19% nuclear, and a small amount of wind and solar generation. Look what's happened over the last 10 years. So a major increase in solar and wind, and a reduction in energy demand. Usually the energy demand is increasing as our economies continue to grow. But the reduction here is due to energy efficiency measures that's taken place. Let's look at projections going forward. Government is saying we've got to decarbonise our industry. How do we decarbonise transportation? The plan is to go to electric vehicles or hybrid electric vehicles. So more electrical generation is going to add to our existing network. And the only place that can come from is the renewable sector. Okay, what's that got to do with me? You may be asking now, you may be thinking, I thought this was about electrical engineering. It's talking just about the UK's energy. Well, let's keep these numbers in mind. Look at the rapid expansion there in renewables. Okay, this is a new and rapidly expanding industry. These are new industries. Yeah, be a part of them. These industries need new people. They need young people to come along and take up the gauntlet of the engineering tasks. Let's think about that 2,000 megawatt power station, Eggborough Power Station. This is a typical 1 megawatt wind turbine. If the wind is blowing constantly every day, 24 hours a day, 365 days of the year, which it is not, it's variable. So we need more than 2,000 to make it equitable to Eggborough Power Station. Okay. And there's plans with the UK government to award contracts for large offshore wind farms, so many turbines, hundreds per wind farm, all connecting back electrically to some offshore substation, which then delivers energy to the onshore. A new and rapidly expanding industry. If we look at the energy conversion process for wind, this is the electrical machine, and then there's these switches here, 6 switches here, 6 diodes here. These are power electronic components. They switch current and control the output voltage of these wind turbines. So this is what's called a voltage source inverter. It's converting AC to DC. This may be a permanent magnet or induction machine. Let's look at that in a system, in a wind turbine system. All of this stuff here is in the top of the tower. So a turbine, a gearbox, an electromagnetic machine, electronics. So there's power electronics, there's analog electronics, there's digital electronics, there's the control of this converter and this converter back offshore or back to the main control point via communication systems. So this is in the tower of the wind turbine. Down the tower goes a high voltage DC cable to the bottom. There's another converter, voltage source inverter, a big box of electronics, a transformer shipping 3-phase power out onto the network undersea, the main collection point. Look at all the power electronics. Look at all the analog electronics, the digital electronics, the communications, the embedded systems. Everything is in this system here. All new, relatively new industry going forward. What about another industry? Yeah, I mentioned electric vehicles. This is what I was interested in. I was interested in these machines here, which drives the vehicles. Nothing new. This was done in 1900. Look, this is a 15 kilowatt electric machine that drives that delivery vehicle, and the range of that vehicle was about 10 miles. Really not significant. When people invented combustion engines, then they just got rid of all this electrical stuff and put a combustion engine on there, and it drove away, and we had faster speeds and longer ranges. What's changed since then? Well, along has come some new magnetic materials around about 1995, 2000, so relatively new in the industrial context. Industrial meaning the knowledge and the use of those materials in industry over long periods of time. Only 20 years long. of applications experience. So not really a long time when we're looking at using these materials. Neodymium, iron, boron, very high energy permanent magnet materials, and also samarium, cobalt, around about 2000. In league with that was the reliable power electronic devices, which replaced this mechanical switching mechanism. And again, the power electronics reliable in automotive type quality and durability. Again, we're looking at 1995 to 2000, so relatively new. And what about the range? So new battery technologies. This was a lead acid in 1900s, a very basic lead acid actually. And then we've got nickel metal hydride, sodium nickel chloride, and lithium-based systems, which have come again relatively new from the 1990s to date. Lithium being the technology that you will find in your mobile phone, for example. Fast forward into now, this is a cutaway of a Nissan Leaf, a total electric vehicle. The engine looks very similar to a combustion engine, but it's not an engine, although people refer to them as engines. This is a box of power electronics, and that supplies electrical power to an electrical machine, and that drives the mechanics of the vehicle. Under the base of the vehicle, there's a large battery storage system. Look at the numbers, 15 kilowatts for that very early electric vehicle, 1900s. We're now looking at 80 kilowatt peak to accelerate that vehicle from 0 to 50 in 8 seconds. So it's exactly the same performance as a conventional engine vehicles. The only limitation at the moment is the limited range, and what government's proposing in the automotive industry is pushing is for maybe we might have a small combustion engine on here as a range extender. So we've got a battery system and a range extender, but that combustion engine might be combusting different fuels. It might be hydrogen, for example, or we may combine or replace the batteries with fuel cells where we convert hydrogen into a very low grade steam and electricity. So new powertrains coming along on vehicles. Just looking at that Nissan Leaf, that's the battery look, maybe about 3,000 to 4,000 smartphone batteries there. Look, imagine 3,000 to 4,000 of these sat under the vehicle, and they're arranged in funny shapes to accommodate the profile of the vehicle. Each of these cells are stacked in arrangements, and maybe 10, 20 of these cells are then managed via electronics. So we've got to balance the voltage on the cells to make sure that they are sharing current equitably. So a lot of this volume here, maybe 10, 20% of it is actually electronic control circuits, controllers, and then an embedded system there, which is like a little computer, like the microcontroller or the processor in your laptop. Imagine one of those sat in some electronics in here, and then sending messages back to the main microcontroller or processor on the vehicle that's controlling all of the subsystems. So lots of systems here, and we may be looking at maybe 80 different embedded systems all coming back to one major overriding management system. Management systems in terms of computing, so the all little processors beavering away doing their separate tasks. Who writes the code for them? Who designs them? Who looks at the system structure? Who looks at the system's integration? How do we connect things together to make sure everything talks together effectively? These are all the jobs of electrical engineering, computer systems graduates. And in the future, that steering wheel there, that may disappear, and this vehicle may become autonomous. When we're driving this vehicle down what's so-called smart motorways now, so when we start predicting better traffic flows, we might be sending communications from this vehicle to central controllers around the road network. So again, communications, electronic and communication systems are expanding on these vehicles. Again, all to try to make the vehicle energy consumption more effective and reduce fuel usage and reduce emissions. So this is the power electronics. If we take the lid off the power electronics, look, there's the power electronic components there, and sat on top of that, there's an embedded system, and right in the middle of that little square there is something very similar to the Pentium processor that you might find in your tower computer or your laptop computer. And there's one for this converter here, and then there's one for other converters, one for other converters. So that there's a range, a number of these on one single vehicle application. So in electrical engineering, we at Huddersfield, we study electronic and electrical engineering. That's power. So we've got electrical power here. This converter is switching up to 600 amps at very high frequency. You know, maybe 15 kilohertz high frequency switching, fundamental frequencies from DC up to say maybe 800 hertz. The mains frequency in the UK is 50 hertz. So with electronics, we can vary frequency, we can control amplitude. So there's the power electronics, the digital, the analog electronics. That's coming back to some computing capability here. So computer systems. We have to manage all of this in a thermal environment. So electrical power, thermal, mechanical courses are all covered in this one particular application, and communications. This drive system is communicating to other components, the vehicle onboard management system, and in the future it will be communicating to systems external to the vehicle. So every aspect of electrical, electronic, and some elements of mechanical engineering are all included in this one single vehicle application. You may not believe that where you are now in your career. You may not think of the automotive industry as a route for you. You may be interested in communications. You may be interested in gaming and software. You may not consider these industries as a place of employment. But look at what's happening with embedded systems and the more electric theme across all industrial sectors. And you will see, if you dig deep into what companies are doing, you'll see that they're all employing the attributes that we study in electrical and electronic engineering. And this is a new and rapidly expanding industry. One of the major problems, the major concerns with the expansion of this industry is the lack of engineering graduates. That is a big concern to the industry, especially in the UK. We have a lack of electrical and electronic engineering graduates that can move into these potentially expanding sectors. If we don't have the graduates, the expansion will be less rapid. We will have imports from overseas, and we will lose some of our industry. So there's a good potential for employment for everybody studying these degree courses. Yeah, but think about it as a career. It's very important. It's going to be a very important contribution to our change in the way we convert energy going forward in the future. Looking at changing energy, then we may want to convert DC to DC, high voltage DC to low voltage DC. On your electrical laptop computer, for example, you may plug into a 230 volts power supply, but on the laptop you don't need 230 volts AC. So you have to rectify that to DC and then switch that DC down to different voltage levels on your laptop. And that might be 3.3, it might be 5 volts, it might be plus or minus 15, etc. So a number of supplies on your laptop. And similar in other industrial applications, we're converting DC to DC. And this is just an example of a DC to DC converter structure built up and tested. Yeah? And they vary from microwatts to megawatts. So I was talking about the wind energy conversion. One movement there is to go to more DC to DC power conversion. So move away from our AC systems to more DC systems in our electrical transmission and distribution. And we're looking at very high energy conversion efficiencies with these electronics. Electronics gives us an edge in terms of improving energy efficiency as we do these conversions. And this is an example of an embedded system now. So here we have a little car and we want to control that car remotely. And this is a student project putting together an embedded system, microprocessor in here, a driver for a power stage that drives motors to drive the vehicle forwards and turn it around. And all of that is then communicated via some communications back to some remote control system. And there's another example. Look at the complexity of these electronics circuits. As you go through your degree courses, then you will start to gain experience on little circuits, then more integrated circuits, and then more complex circuits. So you'll build up over the period of your time studying, you'll build up into more complex systems. And things that look very difficult now, because you're doing them in piecewise progression, you'll gradually become confident, and gradually you'll expand your knowledge, and you will be able to you'll be able to accomplish the implementation of these types of circuits, both in their design, their simulation, and then their hardware implementation and test. Similarly, this is a lower frequency system. If we go to higher frequencies, a new area that's really expanding is 5G communication systems. It's just showing a frequency spectrum, a frequency and gain spectrum, where some elements are trying to log on to this 5G, 5 gigahertz signal here. And these pictures here are part of the simulation of a smartphone to look at the design for its suitability. Does it become corrupted with external interference? Is it an optimized circuit layout? How can we optimize it more to make it smaller, make it more compact? Okay, if we can make it smaller and more compact, we can either make it smaller and more compact, or we can add more things into the same space. So this smartphone here, when I was an undergraduate, would be unbelievable. This will be like science fiction. It wasn't science fiction. There was no such thing. And if I imagined that I could get all of the functions that the smartphone does on this little square of material, you know, it's unbelievable now when you think about it. This has more computing power than the computer that I used on my final year project on my BEng degree. What will be the position in the next 10 years? Think of how things are so rapidly expanding. So this again is a new and rapidly expanding industry. One problem with new and rapidly expanding industries is we have to keep abreast. We have to learn more. We have to understand the technology. And so it's becoming more and more acceptable that going into industry, the expectations are that you will need higher and higher qualifications to keep you at the front edge of technology going forward. Engineers always work in teams. They'll work on their individual work, but ultimately they will work as part of a group. These are just some examples of students in our labs putting together some measurement systems on some projects, doing some tests on a component. I think measuring dimensions that's going into some software programming there. And again, a multiple axis machining mechanism here, electric machines, drive systems, electronics somewhere, and then back over here, look, there's a communications, there's a controller, a computer program controlling all of this equipment. That's for cutting things. It's moving around different axes that can do the machining of a number of, or that would have required a number of machinists to do one particular job. So we can manufacture very complex components that we wouldn't have been able to do some years ago. In terms of undergraduate level, then students, you're not only learning engineering, but a key part of engineering is teamwork. And although you may do individual projects, ultimately in an engineering environment, you'll come together as a team. This is just there's 3 examples of our. We have some fixed MEng projects at master's level, finally at master's level. One is where we have a racing vehicle. We equip the vehicle with a powertrain. The powertrain is designed, the vehicle is designed, built, and then it's tested. Usually at Silverstone in a week's long test trials and testing. Our other project is our Hud Rail. Again, these two are sponsored by the IMechE, where we look at this as a hybrid, actually a hybrid powertrain that drives this scaled rail system. Okay, and you see that the group members here, they all have different aspects to perform on the project. They sometimes have one project manager, or they may rotate the project manager role, and come together, starting from scratch, having very little knowledge of what's happening here, and within the course of a year, they are the experts on that system. These guys here, that you can just see the hardware there. That's a drone system. So there's a drone challenge where we have to lift something off the ground, take it high up in the air, and move it some distances, quite a long distance actually, to deliver a payload. And one of the ideas there is it may be a disaster region where there's maybe some flooding or some earthquake, and we want to take supplies of food or medicines, medical supplies into a disaster region. So we can do that with a remote vehicle. So the remote vehicle, this drone system, has a certain payload, a certain amount of mass it has to pick up and carry over some fixed distance, and that's the challenge. These may be drone type vehicles, or they may be winged propelled vehicles. Quite on all of these all of these systems, there are electrical machines, there's our power electronics, there's energy storage in terms of battery systems, there's the control of that, there's the communications of all of those systems, there's the mechanical interfaces as well, the understanding of the mechanics of these mechanisms. So on all of these examples, or these three examples, they all encompass all of the course offerings that we offer at Huddersfield and are offered at many other universities. So, and it's on these types of projects that you might actually realize really what you're really interested in. So it's very difficult at times when you leave secondary school and you come in, you're thinking about your career at universities. Really, what do you really want to do? But usually you find that out in the first year and the second year. That really focuses you on, yeah, I really want to be electronics engineer. I really want to be electrical power engineer. I really want to be a communications engineer. So at Huddersfield and across many universities, the first year is usually quite a common year where you come in, you get a good grounding, and then you will specialise in the second and third years. This is just a listing of our courses. You can pick them up on our website, but again, it just gives you a flavour for the subjects that we are studying: electronic and electrical power, straight electronic and communication, electronic and computer systems, straight computer systems engineering. Remember that embedded systems type of application there. We have joint courses with mechanical engineering, so energy engineering. So wind energy conversion in terms of the mechanical, the wind turbine characteristics, linking in with the electrical side, the electric machines, the electronics, the electrical power systems, and mechatronics. The project examples that I showed you, MEng, they're all encompass mechatronics, so mechatronic type disciplines that are learned and applied on that course. What about jobs then? Well, these are a number of, we have a very good placement year, and these are just some of the companies who take placement students. They're students who have finished their second year, and then they take a year out in industry, and it's a paid year out, so they get paid as a junior engineer. They're working on an engineering application, and that gives students a year's experience for their CV, which is really good then going forward when they come to graduate. And there's a number of different, look at the companies: BAE Systems, Jaguar Land Rover, that's automotive. What's that got to do with electrical engineering? Well, look at the amount of electrical power, communications, computing, all required for electric vehicles. So look at these companies and look at really what do they do in their core business, and try to look into them and see where are the electrical engineering aspects. And you'll see there's a lot of electrical, electronic communications opportunities in all of these companies here. And what about graduate roles? You know, after a few years in industry, you might be a senior project engineer, quite varied titles: component development engineer, procurement engineer, commissioning, engineering design manager, electronic design engineer, senior electrical engineer, senior electronic systems engineer, control systems engineer, senior quality engineer. So as you progress in industry, then what you will find is you will do your own engineering work, and then after a few years of that, you'll get a little bit bored. You can do that. So then you might take on a project, a bigger project, where you might be working with 2 or 3 more people. You might be managing them. And so you may naturally progress by mid-career into senior management roles. That's what industry is looking for as well. It's looking for senior managers in their industries who are trained in the actual technology that's being applied in their sectors. So have a look at us. There's a contact place for Huddersfield if you're interested. Have a look around to the universities. I mentioned before, one thing that the UK Limited, if you like, is desperate for our new engineers in electronic and electrical engineering. So please think of that as a career. Think about the world without electronic engineering. You'll soon very rapidly see there's lots of opportunities out there.